Right, how's it going, everybody? We are here on Thursday, February 11th, and this week we are going to talk about inverses. And I say this week we're going to talk about inverses because today we're going to talk about generically inverses. In our next video, we're going to talk about the inverses of trig functions specifically. So as our kind of note for today, basically where we wrapped up last week is last week we completed chapter 6. Chapter 6 is the first chapter on trigonometry in the textbook that we're using. And so the thing to recognize is that today is going to be basically be just an algebra day to give us some concepts that we need for some trig stuff related to those algebra concepts in our next video here that we're going to use pretty heavily throughout chapter 7 and throughout chapter 8. So this is kind of the one day where we're going to kind of like depart from our traditional, we'll just like walk through the book that we're going through the sections. I do like our book. Okay, I should say I kind of don't like the ordering of the book for like I don't use this book to teach algebra because I don't really like the ordering of the sections in chapters 1 through 5. I really do think this book has a really good setup of the spread of the sections for all the trigonometry stuff, which is why we do just follow the exact path of the book pretty much for this class. But the important thing to recognize is that this book is written in such a way that the author assumes that you are basically doing the whole textbook. Whereas at College of the Redwoods, we have basically chapters 1 through 5 representing algebra and chapters like 6 through 9 representing trigonometry as two separate classes. Whereas other places separate things or have things kind of combined into like a pre-calculus class, which might in a sense contain all of that stuff like that. There's different ways that people organize content that we all need to be able to get into our calculus ideas here. So the bottom line is that the book is sort of expecting that everybody's seen chapters 1 through 5 if you're in chapter 6 or in chapter 7, but not everybody has seen chapters 1 through 5 since college algebra is not a prerequisite for this class. Which is always a topic of some debate. I generally think that it is typically the case that we advise students that if you have a choice to take algebra before you take trigonometry, but plenty of students are successful in this trigonometry class without having taken college algebra prior to this, as long as you have some algebraic experience. So that's mostly fine. Basically, there's like a couple small algebra holes that we might have to fill in here, and that today is kind of one of those days. So basically, most of our topics in college algebra can be studied independently of the topics that we study in trigonometry, but there is like some overlap of some things that belong to all of the families of functions that are really relevant here, right? In particular, the topic of inverses is something that we can't really go on to chapter 7 without having, and so we're going to pull back to one section of chapter 5 here today to make sure that we actually understand what we need to know about inverses so that we can start chapter 7, since section 7.1 is inverse trig functions. It's going to be awfully hard to understand what the heck's going on in 7.1 if we don't understand inverses in a general sense here. All right. Now, so today is an algebra day. We're not going to explicitly discuss anything about trigonometry in this video. We're just going to discuss the algebraic concept of an inverse. But we really have to have this stuff to successfully transition from chapter 6 to chapter 7. My final comment before we kind of get started here is, in the past, I have had students taking my trigonometry class who had previously taken college algebra. They knew that we were going to be covering essentially an algebra day, and the very first time that I taught this class, I had like half attendance on this day of class because the students who had previously taken algebra were like, I don't need this day. All of those students failed the quiz that I gave on section 7.1 a few class periods later, because it turns out most people don't end up coming away from college algebra with sort of like the important parts of inverse concepts that we actually need right now. So this is just to say, whether or not you have taken algebra, I'm convinced that everybody needs to see all of this stuff here. You're probably going to recognize some stuff if you've taken algebra, but the last 20-30 minutes of today's video is going to be sort of an emphasis on the particular things that we care about with inverses. Sort of, honestly, the trickiest part about inverses is the stuff that we're going to have to pay the most attention to. Some functions, it's easy to discuss their inverses. Trig stuff in particular is never directly straightforward how we think of the inverse of a trig function. So we actually kind of need some of the harder ideas associated with inverses to talk about trig inverses. And so I am quite certain that everybody needs all this content here, whether you've seen topics on inverses or not. So let's go ahead and get started here. So we're going to start with, as we often start with, is a couple definitions that are going to get us through some things. These are definitions that I typically bring up on day 1 and when I'm teaching college algebra. So there's some pretty basic definitions that I think most of us are familiar with, but honestly, I also expect that most people kind of, in a sense, have forgotten some of these things as well here. So First of all, two definitions right here. One is what is a relation, and two, what is a function? A relation is any set or collection of ordered pairs. Bold this so it looks like the other one here. And so what I mean by that is we could write any relation. Maybe I just call it like R right here. It could be a set of a bunch of ordered pairs. So like here's an example relation. Other times we write, and these are implied as XY ordered pairs right here, XY, XY, right? Other times we see relations as more of like blob diagrams indicating, or a mapping diagram, like an X grouping and a Y grouping here, to where we might have things like a 2 and a 3, and maybe it's mapping to things like a 0 and a 4 and a 1, and maybe we like draw some arrows and say, oh, 2 maps to 0 and 4, and 3 maps to 1, or something like that. These are both examples of ways that we like indicate a relation. A function, the thing, and notice by the way, we don't really talk about relations that much in math because we're often much more interested in talking about functions because functions are a special case of a relation, right? So relations are all the collections of xy pairs that there are. Functions are special cases of a relation where there's exactly one output associated with each input. And you should notice right away in these two relations that I have diagrammed out right here, neither of these qualify as functions. Notice in the first one, right? And now again, this is one of those things where I think that everybody has like this like generic definition of function in their head. Most people, even if they've taken algebra, have sort of like forgotten like sort of the specifics about like what it actually really means to be a function. There can only be one output associated with each input, right? Notice that the input of 0 here is associated with two different outputs, 2 and 4. In this first relation R, I'm saying that sometimes you plug in 0 and get out 2, other times you plug in 0 and get out 4. That's not very good for me because that means to me, if I say to you, hey man, I'm going to plug in 0, what am I going to get? Your answer is, I don't know, because you can't tell because multiple possibilities are available to us right here. That's not very well defined, and so this does not qualify as the special case of being a function. Similarly here, the input of 2 has two possible outputs, 0 and 4. I guess I kind of like flipped the situation. Well, whatever. Yeah, similar numbers right there. The point is, in this diagram, there is not only one output associated with each input. The input of 2 is associated with two outputs. If I plug in 2, I don't know if I'm getting out 0 or 4 here. So again, this relation is a relation, but it's not a function because it has the possibility of multiple different outputs associated with at least one of the inputs right here. There's sort of this ambiguity where you don't know what's going to happen in this diagram when you plug in 2. There's several possible outcomes there. That's not consistent. That's not a function. Functions are consistent. Every time you plug in a certain input, you're guaranteed to get the same output every time. We don't have that in these two relations here, right? So it's important to recognize that the relation is really like our most generic description. It's just like XY ordered pairs. A function says, hey, listen, I want there to be predictability. I want there to be consistency. It better be the case that every time I see this certain X value, it's always tied to the same Y value. And we don't have that in the two examples that I've drawn so far. So let's go ahead and look at some examples of these things right here. Given here are four relations. These are sets of ordered pairs. So here's my first set. Second, this is just like four separate examples. I just conveniently, I'm sure all of you guys have had the joy of trying to move around tables in Microsoft Word rather than make four tables. I made one giant table with some blank columns in here to save myself my sanity when I was building this here. So four different relations. And I want to know from you, which of these four are functions? And by the way, I should say, if you're watching this video not live, then you should pause the video right now and you should ask this question to yourself. Run down the list of each of these four and ask yourself, is it a function or not? A function means for every input X, there's guaranteed only one possible output Y. If there's ever two Y values associated with one X value, then it's not a function, right? So if you're watching this after the fact, go ahead and pause now and ask yourself, is that a function for each of these four? Okay, great. Now that you've unpaused, let's go ahead and check your answers here. In the first guy, what I'm seeing is the inputs I see are 1, 2, 3, 4, 5, and 6. These are tied to outputs of 7, 8, 9, 10, 11, 12. Honestly, I didn't even need to see the outputs here. What I'm seeing here is 6 different inputs. I don't even see any evidence that there is ever a x value that I'm plugging in a second time to get a different y value out. So even without even seeing the y column right here, this first relation has no evidence that it's not a function right here because I plugged in 6 unique inputs right here. So I'm going to go ahead and give this guy the check mark right there. Yes, it is a function. For the next table here, I'm seeing our inputs are 1, 2, 3, 1, 2, 3. So it looks like we did come to this machine and give it the inputs individually of 1, 2, and 3 once. Then later we came to the same machine and we plugged in the inputs of 1, 2, and 3 a second time. And what I'm noticing is that one time when we plugged in 1, we got 7. Later in the day, I come and I plug in 1 and I get 8. That's inconsistent. It's not doing the same thing with the same inputs here. Similarly, plug in 2 and get 8. Plug in 2 and get 9, inconsistent. Plug in 3 and get 9, plug in 3 and get 10, inconsistent. All three of this whole second grouping is inconsistent with the first set of inputs to outputs right there. So this is not a function right here. We are inconsistent, right? We need consistency from input to output to qualify as a function. In our third relation right here, the thing that immediately grabs my attention is that we get all this repetition in the y stuff over here, and that immediately causes me to be concerned because we saw this repetition over here caused us to not be a function. However, importantly notice that our repetition here is in outputs. Our repetition here was in inputs. And our definition of function says that we need to have consistency from input to output, not necessarily the other way around. Here I'm seeing, as far as the evidence shows right here, every time I plugged in 2, I got 0. Every time I plugged in 3, I did get 1. I never even repeated any of my inputs here, so I have no risk of not being a function in a sense, right? Although, and I mean, I guess I could change some of these numbers. I'm even going to do that right now. I'm just going to change this. Oh, no, okay, I'm not, wow. Sure, why not? 3 and 4, come on, man. And 5, even now. Why is it doing that to me? Even now, we're still getting that this is going to be a function right here because I plugged in 3 once and got 1. I plugged in 3 again later and got 1. It was consistent. I plugged in 4 once and got 0. I plugged in 4 and got 0. I'm maintaining my consistency from input to output. So it doesn't matter how many days you come back to this machine and give it the same inputs as you gave it the day before, it's going to keep giving you the same outputs as you gave it before. That's what we always want machines to do, right? So this is good. This is a function right here. And it was before. I just changed it to be a little bit more maybe not, but it still agreed with our function definition. Now you should notice that this next example over here is a very similar flavor as the third one did, where we have this column alternating at 0 and 1. But again, it's important that this repetition is now in the x column again. Again, what I'm seeing right here is sometimes when I plug in 0, I get 5. Other times I plug in 0, I get 7. Other times I plug in 0, I get 9. This has terrible inconsistency with our inputs. It does something different with my input, it looks like, every time. Same goes for the inputs of 1. Sometimes you plug in 1, you get 6. Sometimes you get 8. Sometimes you get 10. I have no idea what to predict from this. I lose predictability right here, right? A thing I like to think about when I think about what is the definition of a function is I say to myself, a function is a consistent machine. Think about your keyboard right here, right? And what I want to emphasize to you is the distinction between the example 3 and example 4, and think about your keyboard, all right? Here's the important thing on the keyboard. In example 4, I'm going to just hold up my keyboard right here. In example 4, what we're seeing here is sometimes I press the button 0 and it brings up something on my screen, but other times I press a button and it brings up something else. This is like me saying to you that sometimes I'm going to press the H button and it's going to give me an H. Other times I'm going to press the H button and it's going to give me a J. You would immediately throw away this keyboard. It's not doing its job for you. It's inconsistent. We really want machines to be consistent. A consistent machine is a function. That's bad, right? Same inputs leading to different outputs is bad. Over here, it's completely acceptable that we have multiple inputs going to the same output as long as they consistently do so. It's okay with me that 2 gives 0 as well as 4 giving 0. And my example on my keyboard is that on my keyboard, I have the number 5 up here. There's 5. I know it's too small for you to see, but I know that you guys know that 5 is on the top row. I also have a button that's 5 over here, right? There's 5 again. I don't have any problem with the fact that there's 2 5 buttons on my keyboard. Technically, those are 2 different inputs, 5 here and 5 here, two different inputs that both result in the same outputs of a 5 showing up on my screen, they do that with consistently, it's exactly what I want to have happen. I have no problem with the fact there's two different ways to get 5. The only thing I would have a problem with is if I pressed 5 and sometimes it came up with a 7. That would be the problem. That's example 4 right here, right? So a function is a consistent machine, and I like to think about my keyboard and how my keyboard works to help me remind myself of that. My keyboard is a function. It does the exact same thing with an input every time, and the day it stops doing that is the day that I throw this keyboard away and get a new one because I insist on that consistency, right? A function is a consistent machine. So let's see if we can play this exact same game as we did in this example, but let's play this game with graph instead. So here are 5 graphs, and what I want to know is which ones are functions, right? So playing the exact same game. Is it a function? Is it not a function? The most important thing for us to recognize here is that, now Desmos didn't do this for me when I made my little diagrams, but we know that the horizontal axis is our x-axis, the vertical axis is our y-axis, and that is directly relevant to our ability to answer this question right here. In fact, if we switched which one was X and which one was Y, we would get different answers for this one. So for the first one is, oh, and again, that was a great time for you to pause the video and ask yourself these questions right here and say, can I come up with my yes, no's for these guys right here? In the first one, I'm asking myself, if I go to any one X location, are there any times that I have an X value that's associated with two different Y values, two possible different outputs for an input? Remember that your input axis is the horizontal axis, your output axis is the vertical axis. And I see here, no. Anywhere that I go, any X value that I pick, there's one Y value. Pick an X value, one Y value. Pick an X value, one Y value that goes with it. This seems to be consistently giving me a one Y value as associated with every single X value. And in fact, this is the really easy function right here. Y equals X. This literally, okay, technically that's right, but never mind, what am I doing? I'm going to leave that way. Y equals functions right there. This says whatever your input is, your output also is. If you plug in 3, you get out 3. And we can see that by there being the same horizontal distance as vertical distance to get to any one point on the graph. Right? Now for our second graph, and we can do the same thing. I can say if I go to any particular X value, is there one or more than one output that we get? And I'm just marking some arbitrary X value points, and I'm seeing, yeah, it looks like anywhere I go, any X value that I go to, it seems like there's always only one height on the graph that's associated with that. If I were to draw like a vertical dashed line on any one X value, it's only touching the graph once right here. So it looks like that is going to be a function as well. Every one X value is associated with one Y value. That's important. For those of you that are good with your algebra right here, you'll recognize this as the Y equals X squared function. Now this next graph looks incredibly similar, example 3, to example 2 right here. The only difference is it's been flopped on its side. So now we want to ask the same questions. Is there anywhere where I can plug in an X value and I get two possible Y values? And I want to point out that there's actually 3 different scenarios that crop up right here. One thing you should notice is that with whatever equation this is, it looks like if I were to plug in a negative X value, there's no Y values that go with it. That's okay. That's not any inconsistency. This just says you can't plug in negative x's into this function. There are no associated outputs with negative x's. Another thing I'm seeing is if I plug in 0, it looks like there's only one possible output there. It looks like if I plug in 0, I'm going to get out 0 every single time. However, the bulk of this graph is obviously on the right-hand side, all of our positive inputs, and I'm noticing here, if I plug in this x value, there are 2 different y values that I could possibly be getting out that are associated with that x value. That's our inconsistency right here, right? It looks like this isn't going to quite work out for us the way that we wanted it to right here. This is not going to be a function. Our issue with this graph, notice that these graphs are the exact same graph, but one is flopped on its side. So what that means to me here is it really just looks like this graph opened up along the positive y-axis. This one opens up along the positive x-axis. It seems like these two graphs are the same. They've just switched the role of x and y, right? This is the graph of x equals y squared instead of y equals x squared right here. We've switched the role of the input and the output right here. And notice real quick, if we were to resolve this function for y, we would take a square root on both sides. But again, if you've taken your algebra class, then what you should know is that when we take a square root on both sides, that actually introduces a plus or a minus. So the deal with this, and we're going to explore this one a little bit more in depth in a bit here, is that if I actually looked at this, I really need two different equations. If I'm trying to write a y equals equation, I need two different equations to be able to describe that graph. One equation is y equals positive square root of x, which is itself a function, the top half. The other one would be y equals negative square root of x, which is going to look like the bottom half down there, which itself would be a function. But combined with the two, that's always going to be giving two outputs associated with any one input, right? So input the x value. I look up and down to see what y values I get, and I saw two of them. That's my issue. One x value was tied to two different y values. In this case right here, the inputs of like 4 would be giving me the outputs of both 2 and negative 2. And if I don't know what I'm getting, then it's inconsistent. It's not a function. Very similarly, in our fourth graph over here, it's a circle. Circles are pretty typical geometric shapes out here, but recognize for whatever the equation is that's associated with this, if I plug in this x value right here, there's one possible y value height, and there's going to be a second possible y value height that's also associated with that, right? So here we see one input, one x value, has two different heights that we might end up landing at for our output here. That's not consistent. I don't really have a way to pick between those guys right here. So again, not a function for this guy. And again, part of the issue with this is going to be a squaring deal right here. This is the function x squared plus, okay, so this is approximately, there's some other parts to this equation, but it's essentially x squared plus y squared equals 1. That's the most simple version. That's what we saw, the unit circle equation, right? If we were to solve this for y right here, we would end up getting plus or minus the square root of 1 minus x squared. And again, we're seeing that y requires two different equations to describe it fully. The positive version of the square root, the negative version of the square root right there. So again, individually, the top half of a circle is a function. The bottom half of a circle is a function, but together we're introducing now two different outputs that might be associated with an input, so collectively an entire circle, not a function. Right? Our final graph over here is weird because it's dots instead of like a line or a curve. But I can still ask my same questions. I say to myself, is there anywhere I could plug in an x value and have two different y values? And what I'm seeing here is that x value has one y value, that x value has the same one y value, this x value has the same one y value. That's all legal, right? I have multiple different 5 buttons on my keyboard that all have the same output. I'm cool with that as long as it does it consistently. 0, 0 is clearly a point. Whenever I plug in this x value, I get a different y value. And whenever, the same one though. Whenever I plug in this x value, I'm getting, now there's only one possible y value. So yeah, it looks like in this case, it looks like every x value is tied to only one y value. That's what we need to be a function. Now, my next question to help us answer my question below here for our graphical rule for identifying a function is, my question to you is this: what's the least amount of effort I could do to ruin this being a function? Or really any of these that were functions right here, the first two as well. What could I do here? To ruin this being a function, an easy thing I could do would be, and I'm going to draw this now, but I'll re-erase it so there's no confusion later, is that I could just put another point right there. Notice that if I plop down this point on the graph now when we go to this x location right here, there are two different y values that are tied to it. This y value down here and another y value right here. That would make me inconsistent. It only takes one point. And notice I could do this on any of these graphs. If I had this red curve right here, this is a function. If this point was also a point that's associated with a relation, this is no longer a function because now there's one x value that has two different y values. So there's potential for ambiguity there and or a lack of ability for us to make the right call on what the y value is that goes to the next value. That would ruin us being a function with just that one little point right there. All right. So this guy as it stands is a function, but all it would take is one other point vertical of another point to ruin it. So what's our graphical rule? Well, a typical way that we like to think about this is by thinking about a vertical line. Here I'm thinking about dropping down a vertical line and sliding it along my function here. And maybe I'll go over to Desmos and do a couple of these guys right here and do this with these functions. Over here in Desmos, I can do, let me get back to my standard viewing window right here. I don't want that, I want not pi 21st, I want 1. Oh my gosh, number 1. Okay, here we go. So we've got our ones and our ones. Those don't even really matter. I can look at some of the functions that we just saw, and nicely in Desmos, I can handle putting a vertical line on some things. So y equals x was the first thing that we saw, and I'm going to make a vertical line located at, wait, can I not just, add a slider for A. Oh wait, was that because I was, wait, did I do that right? X equals A? Why does that not make a, wait, what? Oh, I see why it's doing that. That's okay. I can force Desmos to do this in a stupid way right here. There we go. And now I'll delete this one. So now I have a slider bar for A, and the point is this is now a vertical line at X equals A. And what I'm seeing is no matter where I drag it, we're always hitting the actual curve of interest just once. I should do this for us to. There's my vertical line, right? I'm dragging around this vertical line and I'm saying, how often does it hit our curve that we're wondering if it's a function? Since we only ever hit once, there's only ever one output for each input. Then we went and we looked at y equals x squared and we see the same thing. As I drag a vertical line across this graph, it's always only ever hitting the graph one time right here, saying to me there's always only ever one output associated with each input. So we're good to go with that one. But notice if we flip this guy around and do our x equals y squared graph that's laying on its side, now as I drag my vertical line across, I've got no touching points, one touching point right there at 0, but everywhere else it's going to touch 2 times. That means there's 2 outputs coming from one input. That's bad. So our vertical line test says, make sure that you only ever hit, with any vertical line that you could ever drop on the graph, it better only hit the graph one time everywhere. If there's ever a place where a vertical line would hit your graph 2 times, then it's not a function, right? The other one that we had here was like some, I guess what I did was like, it was like x plus 1 squared. Oh my gosh. Oh no, now I'm doing it to myself. X plus 1 squared plus, it was like a y minus 2 squared, I don't know, something like that, equals 1. Point is, there we go, we got a circle down there, some circle, it's been shifted around. And again, the point is, as I drag my vertical line around, no problem hitting 0 times, no problem hitting 1 time. As soon as we're hitting a curve 2 times anywhere, even if it's just at one x value that has 2 y values associated with it, or worse, even more than that, then we're no longer a function. And by the way, we can build some functions that maybe hit even more than 2 times. We could do things like x equals y times y minus 1 times y plus 1 or something like that. Notice this guy right here has that little curve back on itself right there. Here's a case where this is like got a triple issue right there, right? As we go across, we're hitting once over here, we're hitting once over here, but as we pass through this middle chunk, there's actually 3 outputs that are associated with one input here. That's a problem for us, right? Not a function with this guy that we're looking at right here, because in this little interval right here, we've got 3 outputs to every one input. We don't know which of the 3 we should actually be getting right here, right? So anytime we're failing the vertical line test, we're not a function. The vertical line test, says your vertical line anywhere needs to always be hitting the graph just 1 time. If it ever hits more than 1 time, not a function. So the vertical line test is sort of about identifying what isn't a function rather than identifying what is a function. But it's still our kind of rule for that here. So I'll say here the vertical line test, VLT. So again, the vertical line test is more a description of when aren't you a function rather than when are you a function. And this says if you can never hit twice, not a function. 2 or more times, not a function. Right? Cool. So we can identify what is a function now from a table and from a graph. And another thing that maybe you're noticing is that our ability to write an equation as a y equals single equation is very strongly tied to our ability, or our definition of being a function. Here we had one y equals equation, we're good. We were able to write a y equals equation, we're good. Here, if I tried to force the actual equation, x equals y squared, to be a y equals equation, it actually took me 2 equations. And that is associated with the fact that there was 2 outputs for every one input. Same thing here. I can't, my general equation for a circle typically looks like this. If I solve it for a y, it took 2 equations that are y equals equations to describe the circle, not just one. Actually, that's maybe worth showing real quick over here on the graph. I'm gonna do that real quick just to show you. We get the top half and bottom half right there. Our x squared plus y squared equals 1 is the entire circle. But if I solve it for y, I'm going to get things like y equals the square root of 1 minus x squared. And look, there's the top half. And if I stick the negative out front, at the bottom half, notice that individually, that's a function right there. If you look at just the bottom half, it's a function because everywhere we only hit once. Individually, the top half is a function because everywhere the vertical line would only hit once. But when you try and combine them together and make the whole circle, you're going to hit twice, right? So a semicircle, as long as the top half, bottom half breakdown, is going to be a function. The entire circle is not. So again, we can also see our algebraic rule here for is it a function is, and it's not always, we can't always go with this rule, but it seems like it's tied to our ability to be able to write a y equals equation in terms of x. If we can do that, seems like we're going to get a function, but again, notice it doesn't look like I have a y equals equation for this guy, so we can't always do that. So it's a bit more of a soft rule right there, but algebraically, if we can get into y equals form and it's just one equation, then that's good evidence that we're probably a function. So now that we've identified what is a function, what is not a function, let's go ahead and do some things with function using some function notation here. So function composition says, algebraically, a function describes a step-by-step process to determine what output you're going to get based on the input you gave. It seems very reasonable that we might want to perform several successive functions, like an object being manufactured in a factory, right? So what we're going to start to do is we're going to start to think about functions using function notation, so like y equals f of x. And again, like I kind of said right here with our analogy of being in a factory, we might think to ourselves that maybe you're starting with something in the factory where you're going to pass it into the f function right here, right? And as it passes through the okay, I'm going to draw this diagram ever so slightly differently here instead of my like little bouncy curve right there. I am going to throw x into the f machine right there, the f function. And what am I going to get out is I'm going to get out, well, whatever you get from plugging in x into f of x. As you can imagine, being like at a factory, we're going to start with like raw materials and we're going to produce, a pair of Nikes on the end out there. So it might be that the first thing is that you throw a hunk of rubber into a machine and it's going to spit out a piece of rubber cut into the shape of the sole. Then that sole is then going to be the output from the first machine. The chunk of rubber is then going to be the input into the next machine. Then they're going to carve off pieces of it to actually shape up the corners. Then the output from the second machine becomes the input into the third machine, where it might do some glossing to make it shiny rubber. Then that output's going to be the input into the next machine, where it's then going to attach some cloth to it. So the thing that you should be thinking about in a factory line setting is there's several machines that are required to take a raw product, our X value, and turn it into our final product at the very end. And in every machine we pass through, one machine outputs something, and the output of one machine is used as the input into the next machine. So here I'm saying I'm now going to use f of x, the output from the f machine, and I'm going to use this as the input into the g machine. Well, what am I going to get? Well, I'm going to do is apply the g function to the input. So this should be giving me things like g of f of x. This is now my descriptor that says start with x on the inside. That's your raw material. Then apply f to x. Then apply g to f of x. We're working from the inside to the outside when we see these expressions. Start with x, apply f to x to get f of x, and then we're going to apply g to f of x to get, right in a room, g of f of x, right? So all we're doing is layering together a sequence of operations. And again, stick to thinking about an object being a pair of Nikes being manufactured in a factory. There's so many individual processes that it goes through, so many machines that you're sticking something in and pulling something out. And every single step of the way, except for the very first and the very last, you're considering the output from the previous step to be the input going into the next step. And the way that we're always going to interpret our function compositions, this is function notation. This is a composition of several functions. We're composing them together. We're always going to read this from inside to outside. Our innermost component is the raw material we started with. And then first thing that happens to x is f is applied. Once we've applied f, the next thing that happens is g is applied. So we're building from inside to outside. We're sort of digging our way out from the inside parts right here. So let's go ahead and see if we can do some of these function compositions. And again, I want to take a pause real quick and remind you, today is supposed to be about inverses, and we haven't discussed that at all yet. The reason is because we can't talk about what the inverse of a function is if we don't know what functions are and if we don't know how to compose two functions together. And that's why we're talking about defining a function and talking about function composition. These two ideas together are going to show us what an inverse is. So we're leading up to this inverse idea right here. All right. So here I'm giving you three different functions, f, g, and h. These are your machines in the factory. They're going to do things like take in x. The f machine is going to take in x. It's going to first multiply it by 2, and then it's going to add 4 to it, and it's going to give you back whatever the output is. The g machine is going to take in x. It's going to first square it, and then add 1 to it, and then spit it out, give you something. The h machine is going to take in x. It's going to divide it by 2, and then it's going to subtract 2 from that, and it's going to give you the result from that. What I want to know is what happens if we do some combinations of these things, right? So our first example is our most basic one associated with function notation. You should recognize that here 2 is in the slot of x, and h is the instruction set. H says, what operations should I perform? Perform the multiply by 1/2, then subtract 2 operation. So here h of 2 is going to look like, I'm going to say here h of 2 is going to be 1/2 times 2 minus 2. And notice all I did is exactly wrote this statement, except here 2 was in the x slot, so I just put 2 everywhere I saw an x. That's all that happened right here. So it seems like h of 2 should be 1/2 times 2 is just 1. And it seems like h of 2 we're getting out -1 for our answer right there. There's our first answer. Just using a little function notation to describe these guys, right? Now our second example, we're seeing we're going to start with the raw materials, the core most input of 3. The first thing that's going to happen to 3 is we're going to throw it into the g machine. G is going to spit out a new value for us. The new value it's going to spit out, we're going to throw into the f machine as the next layer. F is then going to spit out our final product for us right here, right? So remember, we're always going to work from the inside to the outside whenever we're looking at function composition. Now there's two different ways that I can write out my stuff for this. I'm going to do one of the ways I can think about it for this example, and I'll do the different way for this example right here. These get kind of hairy when we layer together a whole bunch of things, right? This is going to be a 3-layer process right here. So I want to kind of organize my work maybe a little bit differently once we get a lot of operations here. So here what I'm going to think to myself is this. I don't know how to just write an expression for f of g of 3. I just don't know what to do. So I'm going to look in one layer. I'm going to say to myself, well, do you know what a good expression would be for just g of 3? And I'm going to say to myself, yeah, I do, because I have a function for g of x. So it seems like I can say that this is the same thing as f of, and I'm going to replace g of 3 with what I see g of 3 is equal to. G of 3 is equal to 3 squared plus 1. Right? Now, I want to simplify this because I want to know what number this is. This looks like this is going to be f of 9 plus 1, which looks like it is f of 10. Right? So now what I'm seeing is when I plugged in 3 into g, I got 10. Therefore, 10 should be the input into f. So I'm now going to go to my f function. I'm going to use the output from g as the input into f. This is my 2-layer factory situation right here. And when I go to plug 10 into f, I'm going to see that this is going to be 2 times 10 plus 4. That should be giving me 20 plus 4 is going to be 24 right here for f of g of 3. Now, I am hoping that you are kind of recognizing that that was sort of a bit of a clunky way to do this right here in that, there we go, a little bit of a clunky way in which to do this because like, I don't know. I don't want to necessarily do all of my math inside of my expressions right here, right? This could be bulky once we get to lots and lots of layers right here. So I want to show you a way I typically deal with this when I have a multi-layer function composition right here, is I do exactly as I express this. I want to build from the inside out to the outside. So I'm starting with the number 6, and I know that the first thing that I want is I want h of 6. Right? So I'm just going to do that bit of side work. This is like me doing just g of 3 first, where I did it inside of the expression, but I'm now thinking of that as more of like side work rather than keeping my entire whole expression together the whole dang time. So I'm first going to say, what's h of 6? h of 6 should be 1/2 times 6 minus 2, which should be 3 minus 2, which is 1. So h of 6 is 1. So therefore, g of f of h of 6 is really g of f of 1. So now let's do f of 1. That tells me what's my output from the h function is going to be the input into f. The output from f will be the input into g. Right? F of 1 now we can do as 2 times 1 plus 4. 2 plus 4 is going to give me 6. So I've now found that f of 1 equals 6. So it seems like g of f of h of 6 is really g of f of 1 is really g of 6. Right? And now for my last layer, oh, looks like I got to give myself a little more room there. And so now I can go ahead and do my g of 6. And g of 6 is going to be 6 squared plus 1, which is 36 plus 1, which is 37. And so I'm getting for my final answer here that g of f of h of 6 is 37. Right there is my final answer. Right? So in this case right here, rather than keep my entire original expression intact like I did in the second example, I like kept the whole thing, f of g of 3, and I kept like the f the whole way till I used it. Here, this was more like me doing this like step by step, right? That was like step 1, do h of 6. Step 2, do f of 1. Step 3, do g of 6. Then right there, it seems like we ended up with 6 twice. Just so happened that our output from one of the functions looked like the output from another one right there. Right? So I think it's easier often to like organize my work by doing them layer by layer rather than trying to keep everything intact right there. But again, our broad takeaway from this is we're always working from inside to the outside whenever we're dealing with function compositions. Start with the thing you know, the number 6. What am I doing to 6? Apply h. Okay, do that. I applied h to 6 and got 1. Therefore, I can replace h of 6 with 1 to get g of f of 1. Now I deal with f of 1. I found f of 1 was actually 6 again. We got back 6. And so therefore, g of f of h of 6 is just g of, since f of h of 6 turned out to be 6, I got g of 6. And then I did g of 6 to get 37 right there, right? Inside to outside. In the above examples, we performed the specified sequence of operations on a single predetermined input, like 2, like 3, like 6. That was our raw materials going in. We can also perform these same types of compositions of operations on a generic input x. What this is going to allow us to see is what would it look like from a multi-step process into being a single-step process. I know I'm going to have to give myself some more room for this guy. So what I want to kind of suggest right here is that when we start with a generic x and we go, we do the f operation to get to f of x. I'm writing my diagram a little different than I did before. Then I apply g to get to g of f of x. Right? What I'm really thinking is, can we just come up with one step process that's like f? Now, our book's notation for this is they use that open dot. I avoid this notation because I feel like my dot never really conveys the idea that I want it to convey. I always use the layered parentheses for my function notation, but you'll see the book will do that. They'll indicate composition with like an open circle right there. But the point is this, and I'm kind of thinking, again, let's stick to our factory analogy. What a factory worker needs to know is what's F and what's G, right? But do you really think that the person that owns Nike really cares at all about the F machine or the G machine? No. What the owner of the factory wants to know is saying to you things like, hey, listen, I bought this much rubber and this much cloth. What does he want to know? How many pairs of Nikes am I getting on the other end? He doesn't care about what we're producing intermediarily right there, right? What I'm asking is, can we come up with one expression that does the whole dang process for us rather than have to go step by step by step? Could you just say, since I gave you 100 pounds of rubber and 200 pounds of cloth, therefore you're going to get 80 pounds of Nikes? I don't want you to tell me about the rubber cutting process and attaching the rubber to the cloth and putting laces on things. I'm the owner. I don't care about those little tiny details. I care about the big picture resources turning into final product right there. That's sort of what we're doing, is trying to come up with one representative expression that takes us from the beginning to the end without there being any gaps in between out there, right? So let's go ahead and do that. So now I've got the exact same three functions, f, g, and h, but notice that now the expressions of interest to me don't have numbers in them, but they just still have variables in them. So this will give me one expression, right? So if at the end I get an expression that's like x cubed plus 5, that'll say to me, you plug in 5 for your raw amount of resources that are going in. X cubed plus 5 is just telling you how many pairs of Nikes. And it's skipping the intermediary stuff of saying, oh, you're going to get 18 soles and you're going to get 14 cut pieces of cloth, whatever it's going to be, right? Skipping from immediately beginning to the end. As with before, we're recognizing that sometimes I'm just going to do a single function right here. Other times we can compose two different functions. Other times, maybe a raw material needs to go through the same machine 2 times to get to a final result out there. This totally happens in lots of like washing processes where something needs to be washed, dried, then washed a second time. In that case, it's just cycling through the same machine a couple times until it's actually done. It's what I do with my dryer every single day that never dries my clothes on the first cycle, right? I f of x my clothes in the dryer every single time because my dryer never dries things sufficiently. Or I just put in too many clothes that are wet and it can't do it all. Whatever. The point is, see if we can figure out what expressions we're going to get from these function compositions here. Then we're going to start to see, right after this example, we're going to see that there's some special cases that are going to lead us to this inverse conversation we want to have here. So first one that we want to look at here, I want to use 2x plus 10 as my input into the H machine. The H machine says whatever you plug in, x, we're going to multiply it by 1/2 and we're going to subtract 2 from it. So I'm going to exactly follow the instructions that H says. H is a set of instructions. What X is just a placeholder for the input. Instead of using X, I'm actually going to use 2x plus 10, right? This is like me saying like, oh, I can't wait to get my new iPhone 47, which is not true because I would never be one of those people that waits in line for a new iPhone. But this is like me saying like, hey, dude on the street, I'm going to pay you $100 to stand in line here outside of the Apple store for me. That's the X right there, the dude that you're paying $100 to stand on the street. Then when the store finally opens up at 8 a.m. and you want to get your cell phone, you, Mr. or Mrs. 2X plus 10 is going to come and actually take X's place in line because you were paying them $100 to stand in line and wait for you. So now we're actually going to use 2X plus 10 as the input into H instead of just this very generic placeholder value of just X. So let's go ahead and do that here. H is the instruction set that says whatever your input is, multiply your input by 1/2, then subtract 2. My input is 2x plus 10, so that's going to give me 1/2 times my input, 2x plus 10, minus 2. Notice that this is exactly the structure of what H tells me to do. 1/2 times a thing minus 2. 1/2 times a thing minus 2. What was the thing? It was my input expression right here. And I can go ahead and simplify this. I distribute the 1/2. It looks like we're going to get x plus 5 minus 2. And that's going to be giving me x plus 3 as my final expression associated with this guy here, right? So remember that in any function notation, that this x is really just a placeholder. It's just waiting for the actual input to come along and be given to it. I'm saying that rather than my input being the letter x, my input is the expression 2x plus 10, so I plot that into the location in the expression where I previously had x. We can do a similar thing here with our f of g of x, right? I don't know what f of g of x is, so as before, I'm going to work my way from inside to outside. I'm going to say, do you know what x is? I'm going to say, yeah, it's x. Then I'm going to say, do you know what g of x is? And I'm going to say, yeah, it's x squared plus 1. So I'm going to write that. F of x squared plus 1. All right? I replaced the g of x with what g of x is, x squared plus 1. Now I can do exactly what I did in the previous example. I'm going to recognize that f is an instruction set. It's the instruction that says no matter what your input is, what you're going to do with that input is you're going to double it and then add 4. My input is x squared plus 1. I'm going to go ahead and double it and add 4. That's 2 times the input plus 4. 2 times the input plus 4. I'm just mimicking the exact structure of the f of x equation up there. I'm just using a whole expression of x as my input rather than just literally just the letter x, right? Now I can go ahead and multiply this out if I want right here. 2x squared plus 2 plus 4. It looks like we're getting 2x squared plus 6 as our final expression for f of g of x in this case here. All right. Now, I'm going to do this last one again, and I'm going to scroll up real quick here. Up here, I sort of used two different writing strategies. Like I wrote my work different for the second example than I did for the third. And this one is like I did my work piece by piece, and this one I maintained the entire expression and just did the work within the expression. I generally don't encourage this. I feel like people make small mistakes when they do it this way. I like the idea of doing sort of like one little problem at a time, h of 6, f of 1, g of 6. In this way, I wrote 3 easy problems versus doing like one big problem that had 2 parts, right? That's the way I think of it. Similarly here, I'm going to write my work for the third example different than I wrote my work for the second example. Just so you can see a different way to think about this. And again, you can decide for yourself which way you like to write this stuff. This is just a personal preference thing. Consistency is good. We just want to go about strategies that don't make us make stupid mistakes when we know what we're doing. All right, so here's my thought here. I don't know what f of x is. I would like to just write my answer, but I don't know it. So I'm going to stop and I'm going to do the inside to outside thing. I'm going to say, do you know x? Yeah, it's x. I'm going to say, do you know f of x? And here I'm going to do a different thing than I said over here. And I'm going to say, well, yeah, it's f of x. I'm then going to go to the outermost function and say, well, what's f of x? And I'm going to say, well, the f instruction says take your input x. In here, the placeholder is x. I'm going to say f says double your input and add 4. Well, if I'm thinking of my outermost f here, my input is not just x, but it's f of x. So what am I going to do with f of x? Well, the f instruction, and here I'm picturing the outer f on this in the way that I'm thinking about it here, is it's going to say double your input and add 4 to it. So I'm going to do that. I'm going to take my input of f of x, and I'm going to double it and add 4. So here I'm actually handling the outermost f first. And this is just a different way of thinking about this. Neither of these is more right or more wrong than the other. It's just two different ways to get the math done. Right. Now I can say, okay, so I have this expression 2 times f of x plus 4. Well, I want to get this just in terms of x without more instruction sets in here. Well, it looks like here f of x is 2x plus 4, so I'm just going to directly substitute it. And you can see the layering that we see with f of x. I have 2 times x plus 4 plus 4. It's a whole 2x plus 4 jammed into 2x plus 4. It's layered. We've got our functionception going on here. And so this is going to give me 4x plus 8 is distributing the 2 plus 4. And that's going to give me 4x plus 12. So again, realize what we're doing right here. What we're coming up with right here is saying, rather than you having to actually think about doing the operation f twice, we now have a new function, the 4x plus 12 function, that describes the overall result of what you would get if you did f of x, f twice. We could just do this new expression once. So this is replacing a 2-step process, f of x, with a 1-step process, just the 4x plus 12 process right here. So again, this is like saying the individual factory worker needs to know what's f, what's g, what's h, how do I do those things? What the factory owner wants to know is what does like f of g of h look like from beginning to end. He doesn't want to have to do each individual step. He wants to just know, if I give you x as the raw input, how do I compute how many pairs of shoes I'm going to get on the other end? And I don't want to have to think about every machine along the way. And here you can just say, oh, I just multiplied the amount of input by 4 and add 12. That's how many pairs of shoes I'm going to get. This allows us to sort of create a 1-step process from a multi-step process. Right? Know what our answer will look like by only doing one action. Right? That's valuable to us. We've replaced a 2-step process with a 1-step process, a 2-step process with a 1-step process. That's our function composition. Right? Occasionally, something special will happen. So now let's do a few more of these, but we're going to see something unique is going to happen that we didn't see before. So same as before. And now is maybe a good time for you, if you're not watching live, you should pause the video and ask yourself, what do I get when I do these? So you should pause right now and do these on your own right here if you're not watching live. So I'm going to go ahead and do these two function compositions, f of h of x and h of f of x. And I'll do them the two different ways that we did above, right? The first way that we did it is we said, do we know what h of x is? Yeah. H of x is 1 half x minus 2. Now I'm going to say, let's use 1 half x minus 2 as the input into the f machine here, the f set of instructions. And that's going to say, multiply by 2 and add 4. So this is going to say 2 times 1 half x minus 2 plus 4. All right? So I'm going to go ahead and expand here. 2 times a half is just 1, so I'm going to get 1x. 2 times negative 2 is negative 4, and we've got our plus 4 on the end. Well, that just gave me x. And that's really special. Because in this case, what that means to me is, I started with x. H took me somewhere. But what did f do from h of x? It brought me right back to where we started again. It seems like if my initial input was x, and two functions later my final output was x, then those two functions must have been the inverse of one another. It seems like whatever h did to me took me somewhere, f took me right back to where I started again. Let's see what happens when we compose in the other order right here. This is saying, I want to use the same two machines, f and h, but if we think about this as like washing clothes, right? This is like first you put them in the washer, then you put them in the dryer. This is saying first I want to put them in the dryer, then I'm going to put them in the washer. That shouldn't be necessarily the same thing right there. We're mixing the order right here, right? This is saying first I'm going to polish the rubber, then I'm going to cut it. You're not necessarily going to get the same results as if you would cut it first, then polish it, right? So changing the order of our operations here should have an impact on our operation, on the overall results here. So let's do this again. And again, I'm going to use the other writing technique that I did up above, which is to say, let's do the h on the outside first, which is to say, this should be 1 half. What's my input into the h machine? F of x. So I'll do 1 half times f of x minus 2. Now I'll say to myself, well, this should be 1 half of, what's f of x? It's 2x plus 4 minus 2. 1 half times 2x is just 1x. 1 half times 4 is plus 2 minus 2. Oh my gosh, it happened again. So what we're kind of noticing is that h and f clearly aren't things like a washer and a dryer, right? If that were the case, then you would be starting with dirty clothes and ending with dirty clothes, according to this right here. And that's not what's really happening, right? I don't think that's a good analogy for this case right here. Instead, it seems like whatever h and f are, is they're perfectly undoing one another. If you pass x into f, it's going to take you somewhere. But then as soon as you pass that somewhere into h, it's going to bring you right back to where you originally started. It seems like these two things are a nice partner, where rather than taking you somewhere and then just taking you somewhere else, the somewhere else was a special place, the original starting spot back here. So f and h have a special relationship right here where they seem to be undoing one another. Here, with the example on the left, we started with x, we applied the function h to get h of x, then we applied the function f to h of x, and we got right back to where we started, x. Our function composition diagram is going to look different now. So I'm going to scroll up so we can see our comparison. Our function composition diagram looked like we started with we started with x, f took us somewhere, and in this diagram, g then just took us somewhere beyond that as well. What's happening now is a little bit different, right? Because f and h have this special relationship, we're now seeing that x started here, f took us somewhere to f of x, but it seems like what g did is it took us right back to where we started. A different diagram now. So I'm going to say that this is equal to g of f of x. Right? Our function diagram became a loop. Right? So here we say that f and h in this case, oh, I did g again. Okay, I'm going to just write the h so we actually are consistent with the example that we're looking at right here. These letters I'm using very, very, very generically. I mean to, but we might as well have consistency for what we saw happen right there. Right? So here we would say that the functions f and h are inverses because if you start at one of them and then do both, it should get you to back where you started. If we were to have started here, then we would first do h and then f would bring us home. If we started here, we first do f and then h would bring us home. So maybe rather than thinking about things like producing stuff in a factory, a bad example for inverses, because that's like a new thing, a new thing, a new thing, a new thing, a new thing. We're never getting back raw materials. That doesn't make any sense. On the other hand, maybe think about F and H as one is you go to the grocery store, that's F. H is you come home from the grocery store, right? So that says to me, if you start at home, you can go to the grocery store and come back, and you've arrived back where you started. On the other hand, if I joke that if you work at the grocery store, and therefore probably basically like live there, students that work at Winco, right? So if you start at the grocery store, you can do the process of you go home, and then you go back to the grocery store where you're back where you started again, regardless of what you consider to be your starting spot, regardless of the order in which you compose these two things. You always get back your initial input after doing both of them, right? So inverses of one another. So we notate this by saying h equals f inverse of x. H is, that's equals, the inverse of, we use this power of -1 on a function name to indicate inverse. And remember, h and f are instruction sets. They're not like numbers. H and f are the instruction sets of, f is the instruction set that says take your input and multiply it by 2 and add 4. It's a set of 2 instructions, right? And similarly here, we can say f equals h inverse of x because they are inverses of each other. So we get both statements right here. Right? And so some other statements we can make then is that since we saw things like f of h of x equals x, well, I know here, based on what I just wrote with this one, that I can say things like h is really f inverse, right? So I can say f of f inverse of x is just x. And similarly, I could write h of f of x. And I again can say something like h is f inverse. So it's also the case that we could write this as f inverse of f of x is x. So this is generically true of any inverse statement right here, that when you compose a function and its inverse, you're going to get back the original input. So where we're heading to with all this stuff is to make statements that look like sine of sine inverse of x is just going to be giving us back x. Stuff like that. That's kind of where we're heading with some of these statements. Or alternatively, if we start with a sine of x function, we can undo the sign by applying a sine inverse, and that will bring out the x for us. But what we're going to still need to understand is what the heck is the sine inverse function and how does it work? There's going to be some technicalities to this that aren't directly obvious, and we're going to describe those right now. So if f and g are inverses, then f undoes whatever g does, and g undoes whatever f does. They are inverses of each other. It's a two-way street. This isn't just one of the directions. The two underlined statements here says it works either way. Let's use this general concept to find some inverses, and what we're going to find is sometimes it gets a little bit tough right here. So now what we're going to do is we're going to find some inverses, and we're going to realize that there's sort of one major pitfall that we have to watch out for, and that pitfall is going to be closely tied to a pitfall that we need to watch out for associated with our trig inverse functions, right? Some inverse stuff is kind of easy. Trig inverse stuff is not, doesn't fall into the easy campus stuff. That's why we're spending this day doing this here today, right? So let's go ahead and find the inverse of each of these functions right here. And there's going to be two different techniques that I'm going to show you, ways that we can do these guys right here. The first two will do one technique here, one technique here. The next two will do both techniques for both examples, just so that you can see how we think about this. Here, f is the function that says whatever your input is, add 2. Well, how do I undo addition of 2? Hopefully this is a pretty easy one for us to just guess right here. How do you undo addition of 2? Well, with subtraction of 2, right? So I'm going to say here my operation is add 2. So my inverse operation should be subtract 2. Now, there's another technicality to this that we're missing since there's only one step right here. We'll see that in our next problem right here. So I'm going to go ahead and say that our f inverse of x should be taking in x and subtracting 2. Notice if I do these operations one after another, I'll end where I started, right? Start with, pick an x value, 10. 10 plus 2 is 12. I then plug 12 into the inverse. 12 minus 2 is 10. Right back to where we started again. Right? So one way I can find an inverse operation is I can think about what is the action on x and do the opposite of that action. There's a little bit more to it than that. We'll see in the next example. The other way that we can do this is we can think to ourselves that our function notation says to us stuff like y equals f of x, right? Y equals g of x, right? This is just saying to me, when you plug in x into a function, the thing we get out, we typically call our output variable y, right? So another thing that we can do here to identify these is we're saying to ourselves, inverses should do the opposite operations. And so the way that I can describe that is I can say, well, let's treat our input like our output, and let's treat our output like our input. That's going to switch how everything happens out here, right? So I'm rewriting g of x like y, and then I'm going to swap the role of x and y. Now we can resolve the equation for y, and we'll have a y equals equation that should be giving us our inverse right here. So I'm going to divide both sides by 4. And that's saying to me that the g inverse function should be 1/4 x. Hopefully you don't find that terribly surprising. If g is the operation that says whatever you bring in, multiply by 4, the inverse of that should be divide by 4. Right? Now, hopefully that's a sensible inverse. Now, the first two are easy because there's only one piece of action that we're doing here. Add 2, multiply by 4. The next two examples you can see for h and for m are multi-step processes, so we're going to have to be a little more careful. We'll do these both ways. So I want to do the verbal version of this first. What are the operations that are happening to h of x in order? And that order matters. And by the way, you all need to be remembering your order of operations here. It's really important. GEMDAS right here. Grouping symbols first. That'll be relevant down here. Exponents second. Multiplication, division third. Those go together because any multiplication can be written as division, right? Multiplying by 1/2 is the same as division by 2. Addition, subtraction, those go together because any addition can be written as subtraction. Adding -9 is the same as subtracting 9, so I can always swap those out if I want as well. So let's write them out here. Our h of x operations should be, my first thing I do if I'm plugging in x, the first thing is, there's no grouping symbols, there's no exponents. The first thing is deal with the multiplication. So this is going to say multiply by 3. The second thing we're going to do is we're going to add 9. Now to get h inverse of x, we need to not only do the opposite operation like we included up here, but we're also going to need to do the opposite operation in the opposite order. And here's sort of my analogy for this. I get up in the morning, I take a shower. What do? I put on my underwear and then I put on my pants, right? That's the order. What I can't go do at the end of the day is take off my underwear, then take off my pants, unless I'm Derek Zoolander. I guess Zoolander couldn't do it, and it was, oh no, I'm forgetting his name now. What's the, oh man, everybody's got to go watch Zoolander for homework now, I guess. Okay, the point is you can't just take off your underwear before you take off your pants. You have to do the opposite operations in the opposite order. So if it's underwear on, pants on, at the end of the day, we're doing opposite operations, so they're both coming off, and we're doing them in the opposite order. It's pants first, then underwear second at the end of the day, right? So opposite operations, opposite order. This needs to be subtract 9. Hansel, that's it. There we go. Gosh, oh, it's going to bother me all day. Adding 9 turns into subtract 9, and we flip the order. Multiply by 3 should turn into divide by 3. So it seems to me, based on my verbal setup, that my h inverse of x is going to say, what happens to x first? First, we're going to take x and we're going to subtract 9 from it. Then we're going to take the result from that and we're going to divide it by 3. That seems to be what my h inverse of x expression should be. Alternatively, we could follow this strategy over here. I'm going to write this as y equals 3x plus 9. I'm going to swap the role of x and y, and I'm going to resolve for y. And you can see that we're getting the exact same thing right here. All right, so it worked out either way that we did it right here. Got the same answer. We can do the algebraic route, which is probably what we want to do. This is better mechanically, but this is really good conceptually. Opposite operations, opposite order. That's how we identify what is the inverse function. Now let's do the hard one here. This is another great place for you to pause the video and do this one on your own right here. See if your answer agrees with my answer. Let's go ahead and pause now. Go ahead and find the inverse of m of x. This is a little bit tougher here. So I'm going to do this here verbally first, then algebraically. M of x. What are the operations in order that we're performing on x? And I'm going to follow my order of operations. Order of operations says grouping symbols first. So the first thing that happens to x is we subtract 1. The second thing that happens now that we've subtracted 1 is now we square it. After we've squared it, we multiply by 3. And after we've multiplied by 3, we're going to subtract 5. Let's do our opposite operations in the opposite order to identify what m inverse of x should be. So I'm doing opposite operations in the opposite order, so I'm working from bottom to top. Subtract 5 should become add 5. Multiply by 3 should become divide by 3. Squaring should become square rooting. Subtract 1 should become add 1. I'm going to write this one out a little bit differently, by the way, so that you can see kind of what's happening here. And I'm going to build the inverse is what I mean. I'm starting with x. Then we get x plus 5. Then we're going to get x plus 5 over 3 because I've divided by 3. Then we're going to take the square root of that and get x plus 5 over 3, the square root of it. Then we're going to add 1 to that whole expression right there and get x plus 5 over 3 plus 1. This should now be my m inverse of x. Now let's go ahead and do the algebra version and see if it agrees. Y equals 3 times x minus 1 squared minus 5. I'm going to swap the role of x and y and resolve for y. So we're going to have to dig out this y from this kind of gross expression here. So I'm going to add 5. And notice, by the way, add 5 is what I need to do first algebraically. It's exactly what's first over here as well, right? That's not a coincidence. Now I'm going to divide by 3, which is exactly what our second thing says. I want to divide by 3 here. X plus 5 over 3. I'm going to square root. Now, one thing I'm actually seeing here, and this is a bit of an algebraic technicality that kind of actually matters to us though, is that square rooting, if you square a number, if I say a squared number and got 9, you don't know if I squared 3 or negative 3. All right. That's what introduces this plus or minus right here. Technically that is here as well. And now we're going to add 1, exactly our final step right here. So it looks like y is plus or minus the square root of x plus 5 over 3 plus 1. And that's what we're calling m inverse of x. So it's good to see that our verbal route and our algebraic route both take us to the same place. And plus or minus should bother you a little bit right here, though. Let's talk about that a little bit more. So we used two techniques here. We listed the actions performed on x in order, according to the order of operations. We then performed the opposite actions in the opposite order. This is great conceptually, but it's not good like mechanically, right? That's like kind of ridiculous to like make those lists there. But if you want to, go for it. The probably slightly better, more mechanical algebraic thing to do is just swap x and y, resolve for y to get our inverse right there. So let's look at some graphs of some inverses, and the graphs of the inverses are going to kind of show us this like kind of weird thing about the plus or minus that we're seeing over here. So we just found inverses of functions algebraically. Now let's do the same thing graphically. I'm going to give you a graph of a function, and I want to say, can you graph the inverse function? Well, we're just going to follow basically the same set of rules that we identified right here. swap the role of x and y, and go ahead and resolve the equation for y, right? So graphs of these inverse functions. So let's see if we can do that here. Given are the graphs of several functions in the same graph their inverse, right? So here's what I'm going to do. I know that I want to do some swapping of x and y, but it's not directly clear to me how to do that yet graphically. But here's the thing I'm seeing. I can identify some points that are on these graphs. And notice, by the way, I put some grid lines on this one so we can see them. I'm seeing here on this graph, for example, I've got that point there at 0, 1. I'm seeing here we've got points like -3, 0, right? Those are two easy points on this graph. I'm going to use those as my guide points. I'm going to swap the role of x and y. That's an x comma y. I want to graph now y comma x, right? So it seems like instead of -3, 0, I want to graph 0, -3. Similarly, where there's 0, 1, I now want 1, 0. In general, what we're going to maybe come to see, although we're not going to sit here and like do tons of inverse stuff, but the inverse of any linear function is also going to be a linear function. Linear functions only require 2 points to make a line, and so it seems to me like I've got myself a graph of our inverse function right here, right? And if we were to plot some more points, we could agree that we're gonna be in agreement here. Notice, by the way, I'm seeing things like that's the point 3, 2, and that's going to correspond to the point that we have right there of 2, 3, right? So we've indicated lots of points and their inverses. I feel like here's what I should do to be responsible right now. I'm going to get some colored stuff going on right here so that we can see exactly what it is that I'm doing here. That was 0, 1. That was -3, 0. This was 3, 2. There, right? So each of these red points corresponds to one of these black points right there as the inverse point right there. So we have managed to draw the graph of an inverse without even knowing what its equation is, simply by identifying a handful of x and y coordinates, swapping the role of x and y, and regraphing them, redrawing a curve through them, right? So now let's do a bit of a kind of dumber one over here. It looks like we have a function that only exists for a couple places on the graph. It's not like we don't have arrows on the end, right? It only goes from point to point. And it's got like 2 different chunks. So this would be some uncomfortable piecewise function right here. But we should still be able to do the inverse of this, right? So I did label these points on here, but I don't think you can see them. This is -4, -2. This is -2, 0. This is 2, 1. Let me move that one, by the way. I know I'm gonna need to move that guy already right there. I can see where I'm heading with this guy. So let's go ahead and flip each of those points and graph them, right? Now I know that -4, 2, I can swap x and y and get -2, 4, -2, -4. So that guy should be down here now. I can swap -2, 0 to get 0, -2. And I know it used to be that there was a straight line between those 2 points, so I'm heavily anticipating a straight line between these 2 points as well. Next up, I've got the point 2, 1. I'm going to swap that to get 1, 2. And what I'm seeing here is there was a straight line between -2, 0 and 2, 1, so there should be a straight line between 0, -2 and 1, 2. So there's my inverse drawn in red now. It's supposed to be a straight line. Let me draw an actual straight line here instead of a curve. Okay, I barely did any better right there. Whatever, it doesn't matter. We've got a straight line right there. So we've drawn this guy. And notice, by the way, I feel like I'm seeing some symmetry in these graphs out here between my inverse. Oh, I see what I did. I switched my color scheme on this. Okay, that's okay. Uh, Sorry, I swapped my color scheme on this, but I still do have the black versus the red. All right, let's do one more here. And the point of the last one is we're going to feel a little uncomfortable with the last one right here. It's not going to quite go the same. All right, I'm going to get back to my original color scheme. Red curve is going to get red dots on it. So a couple points I'm seeing here. I'm seeing things like 0, 0 is clearly a point. Well, when we invert that, it's going to remain 0, 0. Some other clean points I'm seeing over here are things like -2, 4, and 2, 4. That seems nice and clean to me. Also, I'm seeing points at 1, 1, and -1, 1. Just to avoid clutter, I'm not going to like literally draw the write out those things. But now let's go ahead and invert each of these, right? 0, 0, I'm going to switch and get 0, 0 again. So that's a point also on the inverse graph. -2, 4, I'm going to flip it, and I'm going to get 4, -2. So 4, -2. 2, 4, I'm going to invert to get 4, 2. And you should immediately have a problem with what I'm drawing right now. I'm doing it right, but what's your beef with these 2 points? I'm going to keep drawing here. 1, 1, I'm going to invert and get 1, 1 also. -1, 1, I'm going to invert and get 1, -1. So I'm seeing my points here are forming the same parabolic shape that I was seeing with the red curve, except it's on its side. And we've already talked about what our beef is with this black curve right here. And this last part is going to be a meaningful part about what we have to be careful of with our trig stuff. So we're getting close to our kind of like our concluding idea here. All right. My problem here is that the red curve, I'm going to say in our third example, third graph, the red curve is a function, but the inverse isn't. Right? That's kind of weird, right? The red curve's a function, but when I drew the inverse graph, it wasn't a function anymore. We don't like that. That's kind of a problem for us being able to undo any desired operation, right? And kind of let me point out something. With this being the y equals x squared function, here's a thing that can happen with this. If I start with 3, I can square it to get 9, and I square root it to get back to 3. That worked out fine. If I start with 9, I can square root it to get 3. And if I square it to undo that, I get back to 9. So that worked out. 3 went to 3, that's inverse. 9 went to 9, that's inverse. But notice that if I take -3 and I square it, I get 9. And then if I square root it, well, the square root function is always going to output positives the way that we currently have it defined. So this one didn't work, right? Oops, that's not where that apostrophe goes right there. So it seems like there's something weird about the way that we define the square root function, but the weirdness is actually a good thing for us. All right, let's look at this here. So here's our issue. Our issue is that sometimes when we apply squaring and square rooting, we don't get back to where we started, right? And so what we can do is we fix this issue where the inverse of a function is not itself a function. That's our issue. We want to fix that by restricting the domain of the original function before we take the inverse. We want to identify an interval of x values that produce every possible y value only one time. Notice that this red curve produced all possible y values like 4 2 times. -2 and +2 both produced 4. It's a function, but it's a 2-to-1 function. There are 2 inputs for every one output aside from 0, 0. Right? So let's go ahead and fix this issue with f of x being not 1-to-1. Right? So our f of x equals x squared summary, or sorry, s summary. I'm just reading down there now. There's x squared. But our problem is there are 2 different x values that give us the same y value. And so when I go to invert it, it will fail the vertical line test. So it's not going to be a function. So you should ask yourself, if the vertical line test tells me is my original graph a function, and if to graph the inverse we swap the role of x and y, it should be a horizontal line test that tells me is the inverse going to be a function. All right? Here I can see the horizontal line test says, ooh, I hit 2 times. So the original is a function, but its inverse won't be a function. So what I want to do is I want to identify, is there some region, some x region over which we do only get every y value once instead of twice? And so what I'm going to do is I'm going to identify this region right here, right? If I picked just all the positive x's, then I can graph f of x over the restricted domain to get just this guy. So 0 to infinity is now my new domain right there. X is an element of the interval 0 to infinity. Now when I go to invert this guy, we're just getting what we know as the actual square root function. And you should be kind of weirded out that the square root function is really half a parabola, right? Where's the other missing part? Well, it's the part that we chopped off, that we sort of discarded out there, right? And we want that to be the case because we so much want our inverses to actually be functions, right? So let me show this in Desmos with some cleaner graphs right here to kind of convince you of what's going on, and then we'll summarize what we saw here and see exactly what we're going to need to do when we go to 7.1. So over here in Desmos, what we can see is I could do two things. I can look at my y equals x squared. I can invert it by doing x equals y squared, right? There's my two inverse functions. Ooh, by the way, I did skip over an important thing. Notice that these are mirror images over the line y equals x, where y and x are the same, would be the points that don't move on an inverse, right? 1, 1 didn't move, 0, 0 didn't move. Everything else is mirror imaged over y equals x, so that the x values are the y values and the y values are the x values. That's inverting right there. But notice that the blue curve here, the one on its side, the x equals y squared, isn't a function. The next graph that I want to draw, I want to turn this off right here and show you that if I do graph y equals square root of x, it does just give me the top half. It's not the whole thing. Right? If I turn this back on, you can see that the whole x equals y squared is the entire thing on its side, but since it's not a function, that's not a very helpful mathematical set of instructions for us. We want things to be functions. So what we should recognize here is that y equals the negative square root of x would give us the bottom half. There's the negative square root of x. There's the positive square root of x. Notice that individually, that curve is a function. Individually, that curve is a function, but together they're not. And that's why we have to rip that apart into two pieces right there. So why is it that y equals square root of x is only half of a parabola? It's because if it was the whole sideways parabola, it wouldn't be a function and therefore not useful to us. So the reason that the square root function always outputs only positive numbers is because we restricted the domain of the x squared function to make it 1 to 1 instead of 2 to 1, because we see with our horizontal line test, gosh, I don't know why it doesn't do this for me. Just give me a slider for A and then go back to just doing that. So now notice for our horizontal line test, we have a problem, right? Our horizontal line test says, hey, you're hitting twice, so your inverse won't be a function. So what we did is we came to our function and we restricted the domain and we said, okay, let's pick out just this interval where x is greater than or equal to 0. And now if we only keep that part, notice a horizontal line only hits once on that red curve right there, indicating that when we invert it to get y equals square root of x, that itself will be a function. And that is why our square root function is only half of the square function right there, because we restricted the domain of the square function to make sure that its inverse was also a function, because it's so desirable to only work with functions and not work with just relations. This is a not useful curve here, the purple-black combined one, because I have ambiguity. If I plug in 4, I don't know if I should be getting out 2 or negative 2. That's an inconsistent machine. We don't like that, all right? So let's pop back over here and conclude our summary right here. And let me say here, I want to include one more statement right here that I kind of skipped right here. So basically what we're saying here is this. If the vertical line test says, are you a function? The horizontal line test will say, is the inverse a function? If the horizontal line hits twice, then the inverse is going to be not a function, and that's a problem. So we want to say anytime that we would fail the horizontal line test, we want to restrict the domain so that every y value is only obtained one time, so that when we invert it, every x value is only ever tied to one y value to make it a function. In this graph, I would say that this parabola is 2 to 1 because we hit the horizontal line twice. And again, now in your mind, you should be picturing the sine and cosine. Are those 1 to 1? Are they 2 to 1? Let's look through our summary here. By definition, the inverse of f of x is the function f inverse of x, such that we can compose f with f inverse to get out x. Again, the original. And by the way, we could have flipped f and f inverse to do f inverse then f, and it would still hold true. We can find inverses algebraically by swapping the role of x and y and resolving for y, or verbally, in a sense, by performing the opposite instructions in the opposite order. We can find inverses graphically by swapping the role of x and y, or by graphing the mirror image over the line y equals x, right? We get that graphical, by the way, I'm going to scroll back up and add those vertical, or that y equals x line on there. All right, so we see this mirror image over the line y equals x in each of these three cases right here. Yeah. Right? Every inverse is always a mirror image over the line y equals x right there. So that's your mirror line right there in every case. Right? So back to our summary here. The inverse of a function is not always itself a function, right? We saw that with the squaring and square rooting. When we drew the inverse graph right here from the red curve to the black curve, the red curve was a function and the black curve wasn't, right? We now know that we can identify that by checking the horizontal line test, right? The original function must be 1 to 1, only one input going to each output for the inverse to also be a function. If a function is not 1 to 1, the parabola above was 2 to 1, we can restrict its domain to an interval where the restricted domain function is 1 to 1, where any horizontal line would only hit once. And then we define the inverse only over that restricted domain. That's what we're going to need to do for our trig functions. So looking ahead to chapter 7, when we go to look for the inverses of trig functions in our very next video, we should notice that none of our trig functions are 1 to 1, right? In fact, they're like infinity to 1, right? If I draw my sine curve here, okay, that's negative sine of x, right? I just drew a curve. It turned out to be negative sine of x. Notice a horizontal line is going to hit an infinite number of times, right? We're going to need to fix that. So we saw that f of x equals x squared, it is a function, was a 2 to 1 function. 2 inputs to go with every output, right? 3 squared was 9 and negative 3 squared was 9. That's fine for it being a function, but its inverse wasn't, right? Functions like sine and cosine are infinity to 1 functions. An infinite number of inputs are tied to each output. Sine of 0, sine of pi, sine of 2 pi, sine of 3 pi. All those inputs are going to give you the output of 0, right? There's an infinite number of different inputs I can give, all the pi k's, right? So now you see our goal going into section 7.1. If we want to identify an inverse trig function, then we need to figure out how to appropriately restrict the domains so that we can actually use the inverse function. The inverse won't be a function unless we pick a smart, slim domain over which to define the function. And so that's going to be our goal in our next video, is going to be to say, I want to know how do we define inverse sine, inverse cosine, inverse tangent, all that stuff. But none of those functions are 1 to 1. So all of them, we're going to want to say, okay, what's the smartest restricted domain to where we still experience every possible output one time, and then define the inverse in association with that restricted domain function right there. So again, the point here to me is that, like, when we're talking inverses of linear functions, they're pretty easy. Inverses of linears are linears. Algebraically, inverses of linears, you get more linear functions. 1/3 x minus 3 is another way that we could write this guy right here, right? The algebra is easy. The graphs are easy. Everything works out nice. We didn't have to restrict anything at all. Everything just worked. But it's as soon as we get to these, parabolas are 2 to 1, it became problematic. Trig functions are infinity to one, right? So unfortunately, inverses are easy for some kinds of functions and they're hard for other kinds of functions. And they're kind of hard for trig functions in particular. And that's why it really mattered that we stopped and broke this thing down today, because I think that some of the hardest inverse conversation I ever have to have in algebra and trig is in trig. I think it's easy to mostly discuss this stuff for most of our algebra functions because most of their inverses are functions. Trig functions are not. And so we sort of have sort of the toughest inverse work to do when it comes to trig stuff. So that's, and it's not going to be too bad, but like it's not the easy version of stuff, right? So we're going to pick up in our next video, starting chapter 7, now that we know the algebra we need to know. And in 7.1, we're going to talk about inverse trig functions. We want to undo some trig stuff so that we can say things like, if I say to you, I got sine of x equals 1/2, the way we're going to solve this equation is by applying an inverse sine function on both sides of the equation. But we still need to figure out sort of what this means to us, right? The inverse functions composed together should just be giving us x. And so we're going to want to know, how do we interpret this? Because there's going to be some tricky cases of this that it doesn't work out in a super straightforward sense right here, but we'll get to those coming in tomorrow right here. So stuff like this is our goal for kind of a bunch of chapter 7 here. So I will see you guys for our 7.1 video. Have a good one, everybody.